So in this question, in this problem, take C naught. There's the speed of light in free space, that is 3 into 10 to the power 8 meter per second, and the intrinsic impedance of the medium is 120 pi ohms, and the half surface Z less than 0 is occupied by the air, while the half surface Z greater than 0 is occupied by the material with a medium parameter epsilon equals to 9 epsilon naught, and that is epsilon r is equals to 9 relative permittivity, and your mu is equals to mu naught, and sigma is 0.1 Siemens per meter. Now an electromagnetic plane wave operates at the frequency of 1 megahertz and has an electric field of, this is the expression of electric field, that propagates in air and normally incident upon the interface Z equals to 0. Okay, the first question is determine K naught and the intrinsic impedance eta 2 of the material occupying the half surface Z greater than 0. Okay, so this is basically the boundary, and for Z less than 0, this is air with parameters epsilon naught and mu naught, and sigma is basically 0. Okay, nothing is told about the sigma, and for air sigma is basically 0. Okay, and for the material, that is for Z greater than 0, the parameters are 9 epsilon naught and the mu naught, that is permittivity and permeability, and sigma is basically 0.1 Siemens per meter, right? And the operating frequency is given as 1 megahertz. Okay, so you can find the omega. Omega is basically 2 pi into f, that is 2 pi mega radian per second. Okay, so that is basically your omega. So in the first question you have to determine the K naught. Okay, so K naught, generally K naught is basically beta, the phase constant. Okay, the K naught is a beta, that is in this medium air. Okay, or beta naught you can write, that is basically your omega by Vp. What is omega? Omega is the angular frequency, okay, in radian per second, and Vp is the phase velocity. Okay, so you can easily determine the value of K naught, that is how much? Omega is 2 pi into 10 to the power 6 radian per second, and what is Bp? Bp is the phase velocity in air. It is basically 3 into 10 to the power 8 meter per second. Okay, so 3 into 10 to the power 8 meter per second. So it is how much? This K naught is basically 2 by 3 pi into 10 to the power minus 2. Okay, that is phase constant, and the unit is this per meter. Okay, so for question A, for yes, for part A, it is K naught is basically your 2 pi by 3 into 10 to the power minus 2 per meter. Okay, now second part of question number A, yes, that is you have to determine eta 2. Okay, this is very simple. You know, eta is basically your mu by epsilon. Okay, so eta 2 is basically mu 2 by epsilon 2, means for medium 2 it is basically how much? Mu 2 is simply mu naught, and epsilon 2 is 9 epsilon naught. Okay, so that is basically 1 by 3 mu naught by epsilon naught, and mu naught by epsilon naught is basically means under root mu naught by epsilon, basically intrinsic impedance for free space, that is 120 pi. So this is basically your how much? 40 pi, na? Yeah, 40 pi. So second part is eta 2 is basically your 40 pi. Okay, 40 pi ohms. Now part B, determine the magnitude of the conduction current, that is Jx, that is equals to sigma Ex at Z equals to 0 plus, that is inside the material and arbitrarily close to the interface Z equals to 0. Okay, so next part, now you have to determine the conduction current density at this point, that is Z equals to 0 plus. Okay, and you can see that this is basically your Z axis. Okay, this is Z axis, and so this is Z axis, so you can think that this is X axis and this is Y axis. Okay, so XY is basically Z, so this is your X axis, and okay, and this is basically your z axis. Okay, so this x to y, sorry, this is y axis, x to y, this is z. Okay, so this is y. Now you can see the electromagnetic wave is coming this way. Okay, so like this way. So this green pointer is basically the direction of the electric field, and this is the direction of the wave propagation, and this is the direction of magnetic field in the y direction. Okay, so it is incident normally in this surface. Okay, now in order to find the conduction current density over here, you have to apply the boundary condition. We know from the boundary condition that the tangential component of the electric field is continuous across the boundary. Okay, and you can easily visualize that this particular component, this x component, is basically the tangential to this boundary. This is boundary. Okay, this is basically the boundary. Okay, so this is continuous across the boundary. So you can see the E naught over here, this is E naught, is 10 to the power minus 3, and the sigma is 0 over here in air, so it is not attenuating. So here also the value of E naught is 10 to the power minus 3. Now at z equals to 0 plus, also it will be 10 to the power minus 3. Okay, this is E naught dash, let us assume E naught dash or E naught 0 plus. Okay, 10 to the power minus 3. So you can easily find the conduction current density. Jx is basically your sigma Ex, the magnitude you have to find. So you can take sigma as 0.1 into Ex is 10 to the power minus 3 ampere per meter square. Okay, so yes, conduction current density. So this is how much? 10 to the power minus 4 ampere per meter square. Okay, so for part B, your mod of Jx is basically 10 to the power minus 4 ampere per meter square. Okay, now in part C, determine the skin depth delta of the material in the half space, that is z greater than 0. Okay, oh sorry, okay, yeah, this skin depth. Okay, you have to determine the skin depth of the material in the half space z greater than 0. So as I have already told you in my Facebook page lectures on electromagnetism, that is, you need to remember this particular formula only. Okay, gamma squared is basically j omega mu and into sigma plus j omega epsilon. Okay, and if sigma is very greater than omega epsilon, that is a very good conductor, this is the condition for good conductor, then you can neglect this part. Okay, now let us calculate the value of omega epsilon, that is in this material. Okay, the omega is, we have already calculated, omega is 2 pi megaradian per second, that is 2 pi into 10 to the power 6. And what is epsilon here? It is 9 epsilon naught. So 9 into epsilon naught, what is epsilon naught? It is 1 by 36 pi, standard value you can remember, into 10 to the power minus 9 farad per meter. Okay, that is value of epsilon naught. Now you can see this is, so this is 18 and this is 9 to the 18, so 2. So this is basically 0.5 into 10 to the power minus 3. Okay, this is omega epsilon. And what is sigma? Sigma is basically 0.1, that is 10 to the power minus 1 Siemens per meter. So you can see this sigma is at least 10 times greater than, okay, it's a very greater than omega epsilon, and if it is at least 10 times greater than omega epsilon, then we can assume that this material is at least a good conductor. Okay, so now we can ignore this part. So this you can write basically as j omega mu sigma. Okay, and what is gamma? Gamma is under root j into under root omega mu sigma. And what is under root j? It's a simple thing, you can easily remember. This is e to the power basically j pi by 2 into half, that is pi by 4. Okay, so this is 1 by root 2 plus j 1 by root 2. Okay, so this you can write as omega mu sigma by 2 plus j under root omega mu sigma by 2, that is basically alpha plus j beta. Okay, so what is your alpha? Your alpha is basically under root omega mu sigma by 2, right? Now you have to determine the delta skin depth, that is basically 1 by alpha, so it will be your 2 divided by omega mu sigma. Okay, now you know that what is omega? Omega is basically 2 pi mega radian per second, 2 pi into 10 to the power 6. What is mu? Mu is basically mu naught in the material. Okay, this is basically mu naught. Okay, so mu naught is basically your 4 pi into 10 to the power minus 7 Henry per meter. Okay, and sigma is 0.1, that is 10 to the power minus 1. Okay, so you can cancel 2 and this is 4 pi square, that is 1 by 2 pi. You can take common, so 10 to the power minus 6, and here 10 to the power 10 to the power 6, 10 to the power minus 8, so 10 to the power minus 2, so 10 to the power 2, that is 10. Okay, 10, that is this is basically your 5 by pi delta, 5 by pi meter. Okay, that is your skin depth, 5 by pi meter. So for part C, answer is delta is basically your 5 by pi meter. Okay, now part D, you have to determine the magnitude of conduction current density at delta, at distance delta. Okay, so at x equals to delta, right? Now you know in order to find that conduction current density, you have to find the magnitude of the electric field at that point. So let us assume the magnitude of the electric field over here is Ez dash. Okay, Ez delta. Okay, so Ez delta is basically E0 plus into e to the power minus alpha x. Okay, that is basically your E0 plus. E0 plus is the magnitude over here, that is basically your 10 to the power minus 3. Okay, and e to the power minus alpha into x. X is delta and delta is 1 by alpha, so you can cancel this 2. So this is basically 10 to the power minus 3 by e. Okay, this is the magnitude. Now you can easily find the magnitude of the conduction current density, that is J, say delta, magnitude is sigma into E Z delta, that is basically 0.1 into 10 to the power minus 3 by E. Okay, so that is basically your 10 to the power minus 4 by E. So this is for part D. For part D, it is the conduction current density J delta, that is basically 10 to the power minus 4 by E ampere per meter square. Okay, thank you very much.